So welcome everyone to the OpenCL BOF. We actually have quite a packed schedule for today. My name is Trevett. I'm the VP of Mobile Content at NVIDIA and the OpenCL Chair. I'm going to be doing a couple minutes of intro and context setting. Then I'm going to hand over to Mike Houston from AMD, who's going to give a 1.2 intro, because 1.2 has actually been released since the last Siggraph. We actually launched it at Siggraph Asia back in the end of last year. And Mike's going to give an update about OpenCL and AMD. Then we have Adam Lake from Intel, who's going to be giving us an update on the new open source utility library for OpenCL called Clue. And then last but not least, we have Adobe. Very pleased to have Adobe here. We're going to be talking about how they're using OpenCL for some of the Adobe work that they're doing. So I think most people here are hopefully familiar with OpenCL. Mike's going to be giving us an introduction. So just from a workload point of view and what the working group is doing point of view, the update is there's a lot of work going on in OpenCL right now. We've actually got two subgroups split off the main subgroup. So we have three work groups working in parallel. We have the core working group that's also working on the OpenCL roadmap. We're working on the next version as we speak, an enhanced memory and execution model, just looking to expose more hardware capabilities, making the API and the framework more powerful. But we have also an initiative you might have heard of called OpenCL HLM, it stands for High Level Model, exploring a higher level programming model, potentially single source based, potentially C++ based, unifying the host and device execution environments to make things easier and higher level, where that's appropriate for a certain class of developers. But we're also looking down into the stack. There's another group called OpenCL Sphere, which stands for Standard Parallel Intermediate Representation. It's an IR representation based on LLVM to enable multiple front ends and to enable code obfuscation. And we have news imminent from the OpenCL Sphere group. Their provisional specification is in ratification right now. The group has decided to put out a provisional draft of the Sphere spec for feedback from the industry, including, of course, the LLVM community in particular, before we make the final Sphere spec. So if intermediate representation and LLVM is your thing, watch the skies, because in the next month or two we'll have a provisional spec and we would very much welcome your feedback. Just more for the context, we have OpenCL Compute, OpenGL for graphics. We're gradually building out graphics and compute capability across multiple platforms. Of course, we have GL on desktop, we have CL on desktop, the full profile typically, and an interop between the two. On mobile, we have OpenGL ES for graphics. OpenCL on mobile is interesting. You're beginning to see the first announcements from some of the mobile IP vendors and silicon vendors announcing OpenCL capability. Interestingly, both the full profile in some cases as well as the embedded profile. I think you're going to see OpenCL being pervasively available on mobile devices, probably rolling out over the next 18 months. On the web, you have WebGL, which is a JavaScript binding into OpenGL DS9. We have a good pervasiveness on the desktop, with one notable exception, but hopefully that'll be fixed. And WebCL is bringing compute to the web, a JavaScript API to manage the execution of native kernels in a web browser environment. And just like OpenCL on mobile, I think you're probably going to see WebCL and WebGL on mobile devices beginning to also roll out in the next 18-month time frame. So we're getting a wave of adoption of these APIs. These are enabling developers to use OpenGL and OpenCL across multiple platforms. I think my last slide is the earlier announced OpenGL 4.3. There's an OpenGL BOF at 5, I think it is, this afternoon here. So if you want more details on OpenGL, please come. But one of the things that we announced in OpenGL 4.3 was compute shaders, and I've been getting a lot of questions. Do OpenCL and OpenGL compute shaders compete? I want to make it clear we don't think they compete. There are two separate ways to approach parallel computation that are appropriate for different types of developers and different types of applications. So OpenGL compute shaders, they're fine-grained parallel computation inside the context of the GL pipeline. You're still using GLSL. It typically will execute on a single GPU only. OpenCL, of course, is a much more complete and full parallel heterogeneous programming solution. Full ANSI-C. You can run the code on CPUs and GPUs. You can easily utilize multiple processors. And of course, you still have the coarse-grained interop between OpenCL and OpenGL. So where you're doing a 3D game, you want enhanced shaders. Compute shaders make a lot of sense. If you're doing pure compute, you don't touch pixels. OpenCL makes a lot of sense. In the subset in the middle, the intersection in the middle, where you're doing imaging, video, physics, and AI, it really will depend on how and where you're wanting to deploy your applications. Do you want to write in C, or do you already have an OpenGL application? You can extend your GLSL, which is going to be the right way for you. It's a choice that you have. So, over to Mike here. So Mike is going to give us an overview of 1.2.
Okay, so kind of quick overview again of why CL. It's getting software and silicon vendors to align basically together to go through things. So, as a reminder, Khronos defines open royalty-free standards. Khronos APIs are low level, just above raw silicon. Right? Most of the vendors involved are silicon vendors. It's safe forum for industry cooperation, and there's an IP framework that protects things. Right? There's been a couple of sensationalist articles lately about patents involving OpenCL, but again, the whole point of Khronos is lots of us have patents involved in these technologies. But the point of Khronos is we come together and there's royalty-free reciprocal cross-licensing of that technology so we can move the industry forward as a whole. So lots of people involved, basically every silicon and silicon IP vendor you can think of, as well as multiple software companies, including game vendor. So Neil said this, and I just want to remind people, is that where OpenCL came from was basically trying to figure out an industry standard way to encapsulate processing parallel. So initially we started out with CPUs and GPUs, but there's actually FPGA implementations now being shown, as well as QDSP implementations. The main goal was to figure out one way, one platform that would allow you to find parallel processing for any of your parallel devices in the system. So the big idea of OpenCL in sort of one slide is make it as easy as possible for people to take their standard code, which is generally in C or C++, and move it across to OpenCL. So in a simple example, if you look at traditional parallelizable loop, the easy additions are shown in red, which converts it into OpenCL syntax. Now, obviously I'm not showing the runtime API issues that it actually takes doing to get this to work. But there are multiple solutions. I'll talk about some that AMD is working on, and Adam will talk about other things that make it easier to actually get this code up and running in OpenCL. So the OpenCL working group itself has multiple members. Apple made the initial proposal and is still speculative. But again, the majority of silicon vendors that build hardware capable of doing this are involved in the standard and are very active. Okay, so 1.2 was released, so the spec is out, and full conformance tests were available to the vendors. There is actually one shipping implementation, which is AMD's currently, and there will be others, I'm sure, very shortly. It's backwards compatible with 1.1. There's not any changes here to break anything. So another way to say that is OpenCL 1.2 will run any OpenCL 1.0.1 program. And an OpenCL 2 platform can actually mix devices. So for example, I can have an OpenCL 1.2 platform, but actually put a 1.0 device in there, and it actually all works under the restrictions of that device. We still maintain the embedded profile, and as Neil said, expect to see on the mobile side both full profile and embedded profile solution shipping in the next 18 months or so. We're on a very rapid cadence for OpenCL. So we maintain about an 18-month cadence between the specs, and I don't really see that slowing down. Multiple core implementation shipping, CPUs and GPUs are what usually people see. But again, there'll be mobile and embedded ones coming soon, as well as FPGA ones that have been demonstrated. Okay, so what are the new features in OpenCL 1.2? So device partitioning, this is the best way to think about this is it's a logical subdivision of a device. So you can essentially break a device down into constituent parts, and then you can actually encode to sub-pieces of the device. So, for example, instead of presenting a multi-core CPU as one OpenCL device, you can logically subdivide a quad-core CPU into 4 separate cores and submit to each independent core. Similarly, on some GPU devices, you can actually logically subdivide the GPU and actually get multiple different submissions occurring to the GPU. This allows you to do high priority, low priority mixes between them. So, for example, if you're doing game physics calculations, as well as vertex buffer calculations, you can do those in parallel for submission into your graphics pipeline. Another really big one is that we have separate compilation and linking of objects. So it means that the OpenCL compiler solution now looks a lot more like GCC, in that I can pre-compile and link together things. And this allows libraries to begin to be built, so I can link at code. So third-party vendors like this because it means third parties can now build and ship libraries. A lot of enhanced image support, so 1D images is coming up in GL applications. And we have a lot more sharing flexibility than we used to, especially around texture areas. A new thing is what we call custom devices and built-in kernels. So a lot of the hardware people are on have fixed function units, things like video decode, video encode engines, or some DSP engines. They're not really programmable, but wouldn't it be nice if they lived in the same queuing and event infrastructure as the rest of OpenCL? So that was added in 1.2. And so again, this allows, especially things for video pipelines, to now integrate very well with OpenCL because you now define a way to get to that device. Right? It's a built-in kernel and a custom device. We now have DS9 Media surface sharing. One of the key asks that we got was, hey, I want to use the DXDA pipeline. It would be great if I could process all that in OpenCL. So this provides a way to do that. And there's now DX11 surface sharing as well. So that sort of completes our interaction with the majority of the graphics standards. Okay, the other big thing that's going to be coming out is we're open sourcing our ICD. So there's not really any IP here, it's a trampoline, but this is how multiple vendors can live on a system. More importantly, this allows some multiple open source implementations of OpenCL that are beginning to come up to actually interact with the rest of us, as well as giving people a way, other than using ICD, to load and interact with OpenCL. And so, as you'll see, when I show some examples that AMD has come up with, if you view OpenCL as a platform for other things to be built on top of, having control of how you're loading and managing all the different devices and drivers can be incredibly useful. So it's an optional extension. Not every platform supports this. For example, Apple doesn't use an ICD because they own all the hardware that's in the box. But on Linux and Windows, and even on the embedded platforms, you begin to see the ICD shift. So a little bit about WebCL. So it's still under construction. There's a lot of work here, and there's actually a few sample implementations that are available. I'll show on the next slide you can play with. So it's JavaScript binding to OpenCL. Most of the effort going in is how to deal with some of the security implications. You have raw pointers, which OpenCL has, how do you guarantee security, things like that. Lots of use cases, and it's staying pretty close to the OpenCL standard. There will be some restrictions for security, but it's moving along quite well. The idea how this fits all together, and I'll kind of show the variant on the slide, is so you have the GL ecosystem for visual computing via the web. You have OpenCL, which can interoperate with GL, but doesn't really fit all that well into a browser solution. Now you have WebCL that really fits very similarly to how WebGL fits into the browser to complete sort of the browser-based solution for visual computation. So WebGL plus OpenCL. So it's an open process. So there's actually graph specs up. There's also 2 implementations that are available. So Nokia Research put out one, and Samsung put out another one. And to give you an example of the difference here, so here's a deformation demo, straight JavaScript, to be fair, single-threaded, not fast, 1 frame per second, running on WebCL, offloading onto a discrete GPU, 87 to 116 frames per second. So obviously, the whole point of OpenCL was to get access to the parallel computing resources. This now provides a web-based methodology. Multiple desktop implementations, AMD, Intel, NVIDIA, all shipping OpenCL. All 3 are shipping 1.1 implementations. AMD just shipped their 1.2 implementations. And there's also multiple books So there's the equivalent of the red book, which is really sort of the weird green book. It's very good. It goes through all the consequences of programming. There's a book from Fixstars, and there's now a Japanese translation of the spec, and hopefully there'll be a Chinese translation of the spec out shortly. So lots of resources. So we have these nice little kind of fold-out card that you can download that we have a PDF of. And if you catch things right, we have laminated versions sometimes of these events. There's online mailing pages, and then there's developer forums. Please give us feedback in developer forums. And you can always grab representatives, Adam, myself, Neil, if you have specific complaints or questions that you want. But if you have public questions, please use the developer forums. We do try to respond. All right, so Neil showed this slide. The reason I'm showing it again is I'm going to sort of hint at some of the directions for OpenCL Sphere that AMD has been working on, and Adam will hint on some of the things that came out of HLM that fed into it. So let me talk about sort of a lot of the work that AMD is doing. And one of the things that we're doing is we're helping people use OpenCL as a platform. So not exposing it directly to users, but building things on top of it. Right? And that's what OpenCL was really designed to do. It's a low-level API. Normal programmers are likely not going to be using OpenCL directly. So the first one I want to talk about is what we call Apparapi. I didn't name it that, but I'm naming for it. The short answer is we have a single source Java solution that will actually translate Java bytecode into OpenCL on the fly and execute it on the device. Okay. So we're using Java to target OpenCL. OpenCL becomes the target platform. So we actually run on any OpenCL 1.1 device, including other vendors' devices, because again, all we're doing is translating Java code into OpenCL code to execute on the device. So the way you think about it, you just standard off-the-shelf Java compilers, so Java C out of the Oracle distribution, for example. You build your application. Apparapi is a library that you link into. What you actually end up doing is using an extended version of the kernel base class that you implement its run method. And then inside the JVM, we actually will intercept and actually take bytecode and generate OpenCL, compile it, and run on the device. The other thing that I'll note is if the OpenCL device isn't available, we'll actually switch back to Java thread pool. And the irony is, because of the way that we've implemented this, you'll actually get a speed up over most Java because we'll actually parallelize and thread out your code. Right? We did all the work for CL. So we can move to the thread pool. I'll show some of those results. So, simple example really looks like this. So, kernel class, override run, and that becomes a CL program. And the way that the flow works and how we decide what to do, figure out if the first execution instance of the kernel, does the platform support OpenCL? If it does, then we actually scan through the bytecode to see if we can convert it. We can't convert everything, it's not a flawless solution. If we can convert the bytecode, then we can execute OpenCL kernel on the GPU or CPU or FPGA or DSP. If not, then we go back to the Java thread pool. Same thing if we can't convert the bytecode to CL, we'll go back to the thread pool. If not the first kernel instance, then we see if we have an OpenCL variant. If so, we run it. If not, we go back to the thread pool. So hello world in data parallel compute, nbody. Here's what nbody looks like in Java. Again, there's no CL isms that you see at all in this code. But we will convert this into CL and run it on the device. So to give you an example, there's the baseline, single thread, really slow, doesn't really get any speed up as expected. Thread pool, we actually get almost a linear speed up with the number of cores, especially as the size gets bigger. Then as expected, you throw a big GPU at it, this is a trivial data parallelizable problem, you can get a huge speed up. The main point here is it's very easy to write, integrates into Java, single source solution. And again, it's targeting OpenCL as a platform and execution model, not per se as a language. The other thing I'll point out here is that although this generates CLC on multiple platforms, we can actually generate LLVM-IR directly and load it. And fundamentally, that's what Sphere is. It's a portable IR. We also now have an OpenACC compiler that targets OpenCL from CAS. Again, similar strategy. Take standard C code, add your directives to it. It'll generate OpenCL on the fly, execute it on the device, including all your data management and manipulation. Right. So this is OpenMP, effectively with some tweaks, which is why I call it OpenACC, running on a GPU. Right. And again, it's going through OpenCL, so this runs on anybody's hardware. Last one I'll show, you can see it in our booth on the floor, is a company called Fabric Engine that does a bunch of simulation work. So they have a language called KL. Their CPU variant will target LLVM. You want a solution for the GPU. They can hand the AMD implementation raw LLVM, soon that will transition into Sphere. And then we'll generate into our internal structure and load on the GPU. So again, they're using the OpenCL API, not the language, but all the mechanisms that OpenCL provides to the platform to execute data parallel code on the GPU. And again, you're not writing a lick of OpenCL code, you're writing modular code in their infrastructure. It's a pseudo-programming, pseudo-visual, plug-together thing, and it's up and running. You can go actually buy the AMD booth and talk to guys about it. They do big simulation for all the rendering. So those were my quick examples. I'll hand it over to Adam and see if we can't get the HDMI to work.
Great. So today I'm going to introduce Clue, and this is, as it says here, an open source API for OpenCL prototyping. This is something that was developed by a cross-industry collaboration, so the implication here is Intel's releasing their open source implementation today, but you should understand that a lot of vendors participated in working on this when we recognized the problems that some folks were having getting up and running with OpenCL. And a lot of feedback from ISVs and academics trying to teach OpenCL, these concepts of, context, buffers, devices, memory objects, platforms, trying to wrestle with all that and trying to get, essentially kernel code or GPU code was a lot to deal with all at once. So could we provide a way to kind of ease people in? That's what the solution is. As Mike mentioned, and we all know when we work on OpenCL, is it's meant to be a performance-oriented, low-level runtime. It's not necessarily, and then we imagine that middleware vendors then build tools that application vendors use. And its design goals are different than like sort of ease of use, and Clue's meant to bridge that. So I'm going to talk a little bit about the context of Clue, when to use it and why. And then I'm just going to introduce very quickly the basics of the API and something called the Clue generator. These are the two pieces that make Clue, and it's going to make development and getting started with OpenCL a little bit easier. So the goals of Clue are to simplify three things: program initialization, kernel code compilation, and calling kernels with their arguments. If you've ever used OpenCL, you know the call CL set kernel arg. And anytime you add a parameter to your kernel code, you end up having to go over to your host site code and add another CL set kernel arg, and if you end up having to debug that in 5, anyway, I've had my issues with that myself, so I'm thinking sort of other programmers have as well. This is kind of like visually what I'm trying to say. On the left-hand side, you have a whole bunch of OpenCL code. This is how you would write it before you had Clue. On the right side, you see what it would look like to do the same application with Clue. I have highlighted in red and green the components that are generated or that are part of the Clue API, and I'll get into the specifics of that in a couple of slides. The next question you might ask is, when do I use Clue? You guys have built this. What's the context of using it? I mentioned this a little before. We don't envision this as something that an application that's deployed that might be like an Adobe Photoshop scale application. That's not necessarily what you want to use Clue for. I think for the Siggraph community, we can summarize in one sentence when we think we can use it. If you think that if you understand what DXUT and GLUT provide, essentially OpenCL solution to that is Clue. So when you're, things like getting started, when you're teaching, when you're doing a quick and dirty prototype and you want to kind of do something off to the side of your main application before you integrate it, you might have a little Clue framework, and that's when you use Clue. You wouldn't necessarily use it in a fully deployed, deployed cross OS scenario. Another advantage of Clue that was part of the design that we were keeping in mind is to not build just wrappers around OpenCL objects. So for example, with Clue, the Clue API, if you want to grab the context or you want to pass in a specific context or a specific device that you want to use, there's defaults that if you don't pass anything, it'll pick a default. But if you pass in a specific thing or you want to make sure your code runs on the GPU, it's very easy to do. What Clue is not, just to make sure we're all on the same page, it is not a single source or same source solution. So this isn't something like C++ AMP or CUDA. I mentioned it's not a wrapper. We don't try to extend the kernel language in any way. And finally, it's not an IR. There's been some discussion, they were mentioning Sphere working group. This isn't an IR, and that's a goal of a different working group. We decided to open source this because we wanted to do this transparently so people can look at the code, study it, understand it, and ideally maybe contribute back and make improvements if you find bugs or you find things on your platform that might work better for everybody. The other thing is this is, again, I mentioned a cross-industry effort. Intel's not necessarily going to go out there and make sure it ports and tests across everybody's platforms, but now that it's out there open source, other vendors can pick it up, do the implementation, and contribute back to make files and whatever we need to make sure that it runs across everybody's OpenCL implementations. So if you download Clue, what do you get? Well, it's only 3 files. It's actually 3 files of source code. So it's not fancy. We're not trying to claim we invented some huge, high impact thing here. It's just meant to get started, meant to ease the development, a couple thousand lines of code. 3 files, the runtime has a header and a .cpp file, and the generator. I'm going to talk more about each of them in a couple of slides. We also include all the build infrastructure for Visual Studio in the current solution. If you go pull it down today, you build this in either Visual Studio 2010 or 2012 release candidate. I did that earlier today, it works just fine. There's also some documentation, and I've mentioned that other build environments are coming. Just to show you how simple it actually is, over here on the right, I have it open in Visual Studio, and you see the number of files. There's 3 projects in there, the generator, the runtime, and a simple sample. The simple sample ties everything together, shows you how the generator is used as a custom build step. And the documentation here, just there's a user guide. It's 20-ish pages long, very easy to read. Finish it in 10 or 15 minutes and get started writing code. Now I'll talk a little bit about these basic functions. It shouldn't be any surprise either if something's here that strikes you as, the intent is you're supposed to say, oh, that's all, and that is all. That initialize function takes 500 lines of code and reduces it to 1 line of code. That seems nice to me. The release function, it's the orthogonal function for the initialize, releases any objects internal to the Clue runtime, and then a build source from file and an enqueue call that basically abbreviate the enqueue calls that you would use in OpenCL. You can also request the ECL objects. As I mentioned before, there aren't Clue objects, there's just the CL ones, so there's getters for those. There's some helpful macros for building your ND range to schedule your work, and then there's a couple of functions to call to get platform and device information. I don't know the number of times I've installed and uninstalled different vendors' SDKs from a machine, and I'm like, okay, so what's on this thing now? What does the ICD even see? Well, if you use Clue, you can call one function, say get device info, and it will report all the devices on the platform and give you all their parameters. Another, it's a couple hundred lines of code that you don't have to type in anymore. Just ask, you get a string, write it to a file, pop it up in your editor, and take a look at what's on your platform. Very easy to use. Couple words about the generator as well. Again, simple. Takes your .cl file in, contains 3 things as output. One is the source code, and this is in the header file. And this header file is then included on as part of your host side code. So the kernel is input, the source is output, as I've already mentioned, and it generates 2 functions. And they're designated with CLUG, and the G is for generated. The CLU API just uses CLU as the prefix. And my kernel name is whatever your kernel's name is. So in the previous example of the simple.cl, which had a simple kernel in it, that's CLUG creates simple. So easy to use API. I wanted to get fortune cookies with everybody with this fortune written on it, but I emailed the fortune cookie company to get a custom fortune cookie, and they never responded. So it's not my fault. I tried to get them. Yeah. Okay. Anyway. I'm going back to the example of code that I had on the previous a couple of slides ago, and I just now you can see why there were some things in red and some things are in green. The red are the things that are part of the CLU API, and the green are the Clue generated functions that just have the prefix CLUG. So you can see how simple CLU is to use. Just a slide here on the generator. This is the syntax. If you just say Clue generator, and what the intention here is you can either just include the generator as part of your project, or you can have it already built as an executable, and you can call it with this simple command line interface as a custom build step in Visual Studio or in your makefile. And if you just pass simple.cl into the generator, it'll do logical output files will be named correctly. But if you want to use some of the other functionality, that's here as well. If you think you have some better functionality or other things you want to add to the generator, it's a great place to start, a starting point for that. So, in summary, today, OpenCL development gets a little bit easier with Clue. Allows you to write your first OpenCL application in under 1 hour. This is sort of my own kind of testimonial. The first time I wrote my first OpenCL application, took somewhere between 4 and 8 hours, and most of that time was debugging my host device interfaces and passing the buffers and passing information back and forth. Clue makes that a lot easier. I downloaded the documentation and the source. I hadn't been working on Clue, that was part of a separate working group, and I was able to get that all done in under an hour. You can download it today at where I mentioned. So I'm just going to dive right into a slide or two on Intel's philosophy here, and I'll show a demo if I can try to plug it in time here. Let's see. Yeah, I've got a few minutes. Okay, good. So, Intel today isn't on a slide, but I just want to make people aware that Intel announced today a preview version of its OpenCL SDK for 2013. It's a preview, and it contains, for the CPU side, an OpenCL 1.2 implementation. So for those of you that want to use features like compile and link, or some of the other features that Mike Houston mentioned today, you can download that and get started on that right away. I think also one of the things that is, OpenCL I think started as something that was focused on GPU computing. It's evolving to taking a more heterogeneous perspective, looking at the platform holistically, and the idea is put code that's supposed to be on the CPU, put code on a GPU that's supposed to be on the GPU. You can use a single API to do that. So different things will perform better on the CPU and vice versa on the GPU. So you want to leverage the strengths of your silicon. The other thing that OpenCL 1.2 provides is access to fixed function programmability, and you'll see more from other vendors soon. So with that, I just want to show a quick demo on Intel's Ivy Bridge Ultrabook. Great, okay. So, again, this is just one of our new Ultrabooks, a 3-pound laptop. I love the power supplies now. They're these little pins, basically, you plug in. They're not big and bulky. Runs through an HDMI port. This is an application that was developed with Clue. It's very simple, the classic n-body problem. There's just some particles and some gravity there that's pulling the particles into the center and shooting them out kind of like an orbit around the sun. The other thing to note about this demo is as I said, we used Clue to write this, and the particle updates are actually taking place in OpenCL, but the rendering is done with OpenGL. So we're sharing the surface that we just basically update the vertex positions in OpenCL, and there's no copy that has to take place between OpenCL and OpenGL to write this app. So, it's nice and pretty snappy on what might have, in previous years not have been quite so performant. And now we have this running on our Ivy Bridge laptop. You can see the number, there's quite a number of particles here. I think there's either 16,000 or 64,000 here, all being updated every frame. So, pretty neat stuff. So, I'm going to stop with that, and I think it's time to set up for the next speakers.
I'm Eric Berdahl. I'm from Adobe, and I'm going to be joined today by a couple of my colleagues, Sarah Kong from Photoshop and Dave McGavran from Premiere Pro. And what we want to talk to you about is tell you a bit about what Adobe is doing with OpenCL and what Adobe has been doing with OpenCL. What I want to do first introduce is to put a little bit of context on Adobe's history with heterogeneous computing. Many of you may know that Adobe's been involved in accelerators and accelerator technology for literally decades. About 7 years ago, we, along with most of the people in the industry, started to realize that you can use these graphics processors for more than just graphics processing. And Adobe started a project known as the Adobe Imaging Foundation. And AIF kind of started with this idea that's fairly common now that says, gee, we need software that will let us do for pixels what things like OpenGL do for triangles. Now it seems fairly obvious 7 years past, and we've got many APIs for it, but back then, there weren't a lot of APIs. Adobe created our own software solution for it, our own runtime, and our own programmable language for Khronos. And then in the years since, we've shipped many versions of our software, each with different GPU features. But in the last year, and just earlier this year, we started to ship the first Adobe software that uses OpenCL to accelerate those features. So we're moving now, saying, using open standards and things that more people can use is actually interesting to us. And more importantly, we can start contributing to some of that. Right? So some of the reasons that Adobe is moving into OpenCL, one is it's got an API that's supported across lots of different vendors. Right? So we now can have a single source that will work a lot of places, even on CPUs. We also can use the literally thousands of developers that we have available who are basically C and C++ programmers and turn them into GPU programs pretty easily. And the other thing we can do now is we can take the years that we've been building our own runtime and start contributing them to the OpenCL community directly. So you'll see that Adobe is now a member of the OpenCL working group, and we are helping push and develop the next versions of OpenCL. Okay, and with that context, I'm going to turn over now to my colleague Sarah from Photoshop, and her tell you what Photoshop's doing with OpenCL.
Thank you, Eric. Hi, everyone. My name is Sarah. I'm an engineering manager on the Photoshop team. Today, I'd like to talk about how we use OpenCL to speed up one of the new features in Photoshop CS6 called Blur Gallery. So you can find the Blur Gallery and the filter menu, and the filter, blur, and you have field blur, iris blur, and texture blur. First, I'm going to show you the iris blur. If you want to create solid depth of field, you can use this filter. And on-canvas control allows you to adjust the blur amount. And you can also create some specular highlights called over effects. Next, I'm going to show you the texture blur. So if you want to create an effect like the kind of effect you get with Lens Baby, you can use this kind of filter. And as you can see, it creates a miniature look to your image. This time, I'm going to show you the performance comparison between CPU and GPU. So let's make sure that we have the OpenCL option on. And I'm going to run the field blur. With field blur, you can drop the pins on the image and create put more pins and adjust different blur amounts for different areas of the image. And we have the CPU monitor on the bottom right, and I'm going to hit OK. And it took about 3.5 seconds. Now I'm going to undo this and go to the performance panel, turn off the OpenCL, and rerun this same effect. And this time you see the progress bar, and the CPU monitor shows, oh, actually you guys don't see the CPU monitor, so don't worry about it. Okay, so this time it took 9.5 seconds, so it's pretty good speed up using GPU. So let me go back to the slides. So why OpenCL? So for Photoshop, we want a cross-platform solution, and OpenCL is the only cross-platform GPU solution. There are other GPU programming language like NVIDIA CUDA, but it will only run on NVIDIA card. Why not OpenCL? OpenCL has a steep learning curve, and if you're a C programmer, C++ programmer, it's easier to learn OpenCL and easier to debug in OpenCL rather than OpenGL. And OpenCL also has reached a new level of maturity and ubiquity in the past year or so. So it is now shipped as one of the standard driver on the Windows side for NVIDIA, AMD, and Intel integrated graphics. How do we do it? By the way, for the lens blur in Photoshop CS6, we are using OpenCL Code to run only on GPU. We use the hand-coded on the SSD version on CPU. So we have the SSD version hand-coded, hand-tuned, and imported to OpenCL Khronos. It's about 200 lines of code. And we broke down the image to 2K by 2K chunks to run it on GPU, and I'll explain to you why in a minute. Challenges. Whatever you want to do on GPU, there are challenges. And if you have an image processing algorithm that you are thinking of speeding it up on GPU, there are a few things you might want to consider to see whether it's a good candidate for GPU. For example, is it heavy on bandwidth? Is it compute intensive? Is it highly parallelizable? Lensblur is a good candidate. It meets the criteria. It's also helpful to have an already working debugged C code, since it's always easier to debug in Xcode or Visual Studio rather than debug your OpenCL code. Usually you hear the question like how much faster they put lens on GPU than CPU, and the answer is it depends. It depends on the kind of card you have, the kind of CPU. If you have the latest CPU with many cores and a low-end GPU card, then the performance gain might not be significant. There are resource limits to be considered. There's a timeout issue on both Mac and Windows. So if your code runs a long time, then the OS will kill your process. There are memory issues. So on GPU, there's no virtualized memory. So if you're processing screen size image, if you know the number of pixels you're processing, it's great. But Photoshop has to support arbitrarily large images, and you may be processing 2 GB image. So we have to break up the image into 4K by 4K chunks to process it on GPU. There's also, we also did the bandwidth test to enable the OpenCL option in Photoshop. And the bandwidth test might not be accurate, especially on mobile GPU. When GPU is in low power mode, then the number you get is not accurate. There are platform variations, so we don't know what kind of drivers users have, and when we run into issues, then we prompt the user to update the drivers. And again, there are various compilers, AMD, NVIDIA, Intel, Apple, and your code might compile on one platform and might have compiler issues on another. Future plans. So with all those challenges, we still think it's worthwhile. So we are going to be using OpenCL for Mode image processing for our future version of Photoshop. And we have done some preliminary work, and there are some promising results using Intel auto vectorizer to use OpenCL on CPU. So we will be looking into that. With that, I'm going to hand it over to Dave McGavran from Premiere team. By the way, I'm hiring, so if you are a strong programmer with image processing background, please come talk to me.
Hi, so my name is David McGavran. I'm the engineering manager for Premiere Pro. And about a year ago, we were trying to look at what we should be doing next for performance. So the Premiere team has a long history with GPU performance enhancements, and we worked very hard to make sure that Premiere works really well on the GPU. So Premiere, as a little background, is a video editor that edits native video formats. So we edit, HD, SD, 4K, 5K, red footage, ARRI raw footage, all native. And what we wanted to do this year, what we really wanted to focus on, was basically bring a lot of what we do onto the laptop range. And so a lot of our customers have the Macintosh 15-inch laptop. It's a very popular video editing laptop. And so we wanted to focus on how to get Premiere Pro running amazingly on, this is going to be hard to demo at this resolution. So we wanted to really make sure that our mobile users can get performance that's unbelievable, and we want to have some new features. So this is Premiere Pro CS6, and this is a 15-inch laptop from 2011 with an ETI card in it. And what you're seeing here is 4 HD streams of video. Each of these has a scale and position on it to bring it down into that 4x4 block. So in CS6, we wanted to look at not just making things faster. We're pretty fast at getting kernels to go, effects to work really fast and video editing to work really fast. We wanted to change the way people can actually edit video, especially when you talk about what you can do on a laptop. So here we have, I'm going to show you a couple new features. We have, again, 4 HD frames of video, composited together with a scale to get them into that picture-by-picture look. And we have a new feature called adjustment layers, which you may be familiar with if you know Photoshop. So what we're going to do is we're going to add a color corrector to this adjustment layer. And what that's going to do is allow you to grade, to change the color of all those videos together at once. So instead of doing a 3-way color corrector on each individual one, you can do it on all of them together. So when I go and actually do that effect, we can now, as you wait for a second here, you'll see that the color of that video changed on all of them. So that's now a 3-way color corrector operating on all those video screens. But that's not really what our customers want. They want to change the way they can edit, and we're going to use OpenCL on this laptop to do that. So what I'm going to actually do is go turn on the OpenCL mode. And what you're going to see here is as I start playing now, I can actually start editing that effect in real time without dropping frames. So now we're doing a color correction on 4 streams of HD video, and that's pretty cool. Now that's not something that was really possible before, and I'm not stopping when I'm editing. But that's not it. I can actually go in and continue to edit, so we're not stopping playback, and I can just go down here and I can add, say, a brightness and contrast to that adjustment layer. And I can go down there and I can now start editing that. And now you can see that I'm changing the brightness and contrast on all those videos. But that's not it, actually. Each of these layers here also has a 3-way color corrector on it. So if I actually can see my screen, I can go find another one of those layers here, and again I can start editing that layer in real time. So here you now see the bottom left-hand video changing with color. So what we have here is 4 video streams with scales, effects, positions, all together on a 15-inch laptop, playing in real time, changing the parameters without stopping playback. That's where we can use OpenCL to change the way that end-user applications work. So you heard by Eric and all the other talkers, and Sarah said that we wanted to use OpenCL. Basically, our developers can learn this easier. It's something that we can do on multiple platforms, and it's basically, it's a great technology that works across vendors, across platforms and everything. So here, so how did we get to this point? So Premiere's been working on performance, like I said, for quite a long time. So a long time ago, we started realizing that everything has to happen in parallel for something like that to work the way you just saw it. So we break up our entire pipeline into multiple stages. So we have threads for disk I/O, we have threads for CPU processing for the few things we don't do on the GPU, which are like H.264 decodes or other basically debayering techniques. We have an upload node, and we have the GPU processing node, which all happens in parallel. And then we also have the display and or export path, depending on whether you're rendering or whether you're going to the screen. So, like I said, we started on the OpenCL port a year ago, and our plan was to get 5 to 8 OpenCL kernels working. We were kind of pessimistic. It was relatively new technology. We didn't know so much about it. This is what happens on OpenCL and CS6. We have all the things that happen behind the scenes on the GPU. So we have adjustment layers, like I showed you, color space conversions, deinterlacing, compositing, all the stuff that happens to video that the user doesn't see. Then we have all the transitions and effects that the users themselves manually add. This basically means that almost the entire video processing pipeline that you just saw is actively working on the GPU on this mobile platform. So that's pretty impressive. We got a little bit further than we thought, and this was under a year's worth of work. We started this last June or July, and we shipped it in May. So, that really shows that OpenCL is here and ready to go. So we were pretty happy with that. So what did we do? So there's an interesting thing. Not only are you running on the GPU, we're actually improving the quality of what the user wants. So on the GPU, instead of a traditional 8-bit video processing pipeline, we have an entire float pipeline. So now we're getting better quality. We're also getting deeper support when you have the correct hardware, so 10-bit displays if they're available. If you're mixing some effects that aren't GPU accelerated with effects that are GPU accelerated, we'll actually chop up those sections of the pipeline and do the GPU ones up on the GPU, and we'll do the software pipeline for the stuff that isn't on the GPU, which means we don't have to port the entire application at once. And then we do all this with OpenGL interop so that we get that high performance display. One of the interesting things about this is when you start looking at the point-wise filters, things like brightness and contrast and some of those others, what we realized we had to do is that to get that to work in that quality that you've seen, we actually do some manual concatenation. So we take all those effects, or a good subset of those effects, and concatenate them into one kernel. And then we can read once, apply all those effects at once, and then write once. So that's basically a huge bandwidth savings and allows you to keep stacking effects without falling down. So we have almost the entire pipeline working on there. So what's next? What things are we brainstorming about that we can do in the future? There's still a few effects out there that we haven't ported. There's not many. But there's more. There's also effects that we could do in the future that really wouldn't be practical on the software side. It wouldn't really make sense. There's things that you can do that, more interesting science fair projects on the GPU. Right now, we don't have a really way for third parties to get into our GPU processing pipeline. We want to address that. We want to actually consider whether it makes sense to do GPU encoding and decoding up on the GPU. There's interesting trade-offs there because we do everything on the GPU. The new CPU is sitting idle. OpenCL is a great way to start looking at some of those solutions. We want to add multiple GPU support if that's possible. There's a lot of big machines out there that editors have. And then there's some other things, Premiere-esque that makes sense to do up on the GPU. So there's lots of stuff we can still work on. So that's the main part of my demo. I do want to actually show you something that hasn't been seen yet. It's a technology preview. That's important to know. So when we shipped OpenCL, that was a lot of work in 1 year's time, so we had to be very selective about where we shipped it. We weren't able to basically qualify it where the Photoshop team was, so we only turned on OpenCL on that one MacBook 15-inch laptop with the API card. However, as we know, OpenCL is portable, and so what we'd like to do, and we've done this with other technologies in the past, is we'd like to basically make sure that these cards really work before we let our users have them. So we're going to do a quick little technology demonstration here. If it works, this was causing problems before. This is the new MacBook Pro, which no longer has an API card in it, and now has an NVIDIA card in it. So here you're going to see that same demonstration working. Now not on the certified card which we focused on in the past, which was an AMD card. This now also has OpenCL running on the newest laptop with an NVIDIA card. So this, this really shows why we chose OpenCL. This gets you that cross-vendor support, the write once, how to work multiple places. This is really where the benefit is for our customers, is that we can really focus all of our effort on one set of technology, and our customers will get this across multiple vendors, multiple platforms, and all stuff like that. So I do think we are now out of time, so we don't have time for Q&A, but I know at least the Adobe people will probably hang out outside for a bit if there's any questions or information there if you want to take Sarah up on her offer. You can come and find us outside. Thank you.